you're listening to the Science of Everything podcast, episode 74, Minerals and Rocks. I'm your host, James Fodor. In this episode, we're going to take a look at rocks and minerals. So we'll start with looking at minerals. We'll define what a mineral is, and look at some of the properties of different minerals, so crystal structure and habit, hardness, lustre, cleavage, and things like that. And then I'll go through just some of the main mineral classes, in particular the silicates, halides, sulfides, oxides, some of the other main types of minerals. And then I'll move on to start talking about rocks. We'll give a brief definition of rocks. We'll look at the three main types of rocks: igneous, sedimentary, and metamorphic. Some of the subclassifications within each, and a few of the different properties and other interesting tidbits. No particular recommended background for this episode, although some basic knowledge of chemistry, so for example, the sort of thing that I talk about in episode 8, atoms and molecules, would be somewhat helpful for some of the discussion about minerals. Okay, so let's make a start. So, first of all, starting with minerals. You've probably heard of minerals before. You may have heard of them in the context of vitamins and minerals. That's a nutrition context. The definition of mineral there is not the same as the definition of mineral used in geology, so it's the latter that I'm going to be focusing on here. In geology, a mineral is a naturally occurring substance that has a specific chemical formula and a crystal structure, and it's inorganic. So those are the four traditional properties: inorganic, specific chemical formula, naturally occurring, crystalline structure. However, some of those have come under some dispute or debate recently, particularly the having a specific chemical formula and being completely inorganic, that is not derived from biogenic processes, because there are some minerals or mineral-like substances that are biogenic, and there are others that have some variability in their chemical formula, so those are somewhat ambiguous requirements. Naturally occurring and crystal structure, though, are essential. So if something's man-made, it's not considered to be a mineral. Having a crystal structure means that the atoms are arranged in an orderly lattice-like arrangement structure. So glass, for example, is not considered to be a mineral. Well, it's generally man-made for starters, but secondly, it does not have a naturally occurring, it does not have a regularly structured crystal arrangement of the atoms. They're sort of jumbled together in an amorphous structure. So the concept of mineral isn't necessarily extremely well defined, but it's a useful category. I would say it's probably not something that is sort of given to us by nature, because really there's just different mineral combinations of atoms and compounds. But the study of minerals is a well historically grounded discipline, so it's a useful concept to have. So basically, when we think of mineral, think of a naturally occurring crystalline structure. A mineral is not the same as a rock. We'll get to that later, but a rock can be comprised of many different minerals, and a mineral in turn can be comprised of many different atoms and compounds. So think of it as a sort of hierarchy: atoms, molecules, then minerals, and then rocks. So now that we have some idea of what minerals are, let's talk a bit about the different physical properties of minerals. This is one of the key things we want to know when we have a mineral sample or are talking about a new type of mineral. What are its physical properties? So there are a number of different physical properties of minerals that are typically of interest. The crystal structure is the most basic, essentially, because that defines the structure of the mineral. So all minerals have a regular crystalline lattice arrangement, and that means that there must be a certain symmetry to the arrangement of the atoms or compounds that make up the mineral. Symmetry is really a mathematical concept. You can think of it, an arrangement as being symmetrical when you can do something to it and leave it looking the same afterwards. So, for example, if you take a square, if I rotate the square by 45 degrees, then it looks like a diamond. It's not the same. So it doesn't have a 45-degree rotational symmetry. But if I rotate it by 90 degrees, then I rotate it around sort of by one full side, it looks the same again. So it has 90-degree rotational symmetry. If I just drew a random, strange, blob-looking shape, that probably would not have 90-degree rotational symmetry. Now, if I imagine a circle, that has any degree rotational symmetry. No matter what degree I rotate the circle about its central axis, it looks the same. It doesn't change. So you see, different shapes have different types of symmetries. And that applies to 3 dimensions just as well as it does to 2. So different crystal structures can be described and defined by the types of symmetries that they have. This can be studied mathematically. It gets quite complicated. We're not going to go into details. I just want you to get the idea that different crystal structures can be categorized according to what types of symmetries they have. And so we have a number of crystal families: isometric, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic. I won't really describe exactly what the difference between those are. The main point to get is that they're classified according to whether the side lengths are the same and whether all the internal angles are the same. So, for example, if you had a cube, all the sides are the same, all the internal angles are the same, that would be an isometric crystal structure. Triclinic is the opposite extreme, where all the side lengths are different and all the internal angles are different. So you can think of that as a sort of an irregular prismatic structure with all different sides and angles, a bit hard to explain. And then all the ones in between sort of have various different combinations of same sides and or same angles, some the same, some different, like rectangular prisms and things like that. That's the hand-wavy way of explaining the difference between these crystal families. And this is important because the crystal family that a particular mineral belongs to will have an effect on some of the other physical properties, as we'll see. One property of minerals that you may be familiar with, it's one that for some reason people just seem to know about, it's taught in primary schools or whatever, is hardness, Mohs scale of hardness, which runs from 1 to 10. Talc being the lowest and diamond being the highest at 10. Now, hardness is a property that defines how much a mineral is resistant to scratching. So basically, if you get two minerals and you scratch one along the surface of the other, the question is, does it make a mark? Does it make a permanent scratch? If it does, the mineral is set to scratch the other one, and therefore it's harder than the other mineral. So diamond scratches everything, so that's why it's the hardest at 10. Talc doesn't scratch anything, none of the other main ones anyway, and so it gets a value of 1, and the others in between. Mohs scale of hardness is only an ordinal scale, so it just says what scratches what. It puts them in an order, but it doesn't give any absolute value as to how hard they are. There are other scales which do that, which put them on an absolute level, but those tend to be much more esoteric. I want to point out also that diamond is not the absolute hardest chemical substance. It's just the hardest mineral. So remember, minerals are naturally occurring, and we have been able to create synthetic substances which are harder than the diamond, but they're not minerals, so because they're not naturally occurring, so they don't displace diamond on that scale. Another important property of minerals is lustre. So that basically refers to how reflective the surface of the mineral is, how shiny, essentially. And there are different words that are used to describe lustre, depending upon the exact qualities of the shininess or the external appearance of the metal, basically. Some minerals don't have lustre, so that's called a dull or an earthy lustre. They kind of look like, well, earthish, sort of. Not necessarily earth color, but that sort of textured, not shiny appearance that earth has. There's some that look kind of greasy, some that are metallic, so they look like metal, some that are pearly, resinous, silky, vitrinous, which look kind of like glass, waxy. The luster of a mineral is often determined by, as you would expect, the crystal structure and the chemical compounds that make up the minerals. So there's often a lot of interesting, even quantum mechanical effects that can go into determining both the color and luster of a mineral, which, based on how exactly the light interacts with the mineral structure. Again, I'm not going to go into the details of that, just to give you a sense of it. Recommend looking up luster or mineral luster on Google Images so you can see some examples of these. I'll post some up onto the Facebook, as I tend to do. Another property of minerals is, one of the most obvious, is color. Now, color is a tricky one because it's typically thought of as a non-diagnostic criteria property. So what is meant by that is that when a mineralogist is looking at a mineral sample, they'll try and identify what mineral it is, what collection of minerals it might be. So the luster could be one property that they'll use, what it looks like in terms of how it reflects the light. Hardness could be another one, and there are some others as well, like streak and cleavage and habit that we'll get to. Specific gravity, basically how heavy it is. But color is typically considered to be non-diagnostic. In other words, you can't tell what mineral a sample is based on what color it is, in general. Now, the reason for that is because the color of minerals is often determined by small impurities within the mineral structure. So small quantities of iron or aluminium or something like that. Anything really it can be that significantly affect the color. A really good example of this is ruby and sapphire. So ruby and sapphire are actually the same mineral. They're both corundum, which is actually 9 on the Mohs hardness scale. So really they're the same. They just have slightly different impurities within the mineral structure, which lead them to be red and green respectively. They're not different minerals. So that's an example of how color is not diagnostic. So it's not very useful in most cases to see what color a mineral is. Although there are a few notable examples, like gold, for example. It has a fairly distinctive color, but for the most part, color is non-diagnostic. Streak is something that's related to color, but is more useful. Streak refers to the color of mineral in powdered form, which is often different to how it looks in the body crystalline form. And that's often more useful. So a common way of determining this is to take the rock sample or the mineral sample and literally streak it along a slab of porcelain and look at what color it is there. So that grinds up a small proportion of the mineral, so you can see it in powdered form and look at what color it is. And that's often more useful than the color of the body mineral. Another property that I mentioned earlier is crystal habit. It's a little bit of an odd name, but it refers to the basically characteristic external shape of a crystal or a mineral sample. Now, it differs from lustre in that lustre refers to sort of the shininess of a mineral. It doesn't have to be shiny necessarily, but it's how it reflects the light. Whereas habit refers to the shape. So I guess one way of putting this is that lustre would really just require you to look at it, whereas habit, at least in theory, you could tell by just feeling it, I guess. So that's the difference. Often, as a novice, and I'm a relative novice, these sorts of things, it's somewhat difficult to discern whether the difference between crystal habit and color and lustre, because they're kind of all mixed together when you just naively look at it. But when you get more practice with this sort of thing, you can distinguish the difference between color and lustre and habit and some of the other properties. Anyway, crystals have a very wide range of external appearances, and again, I'd recommend doing a Google search to see this. I won't talk about all of the technical names because they're hard to pronounce, but I'll just give you a sense of them. Some crystal forms form needle-like tapered projections where they literally look like pincushions or porcupines. They're kind of scary looking, actually. Others have like almond shape, knotty sort of a structure to them. Some of them have a grape-like protuberances to them, so hematite's an example of that. They look quite odd, actually. Some are more columnar, others are more cubic in shape, look like almost a ball cube if you're familiar with Star Trek. Some are dendritic, so they have tree-like structure. Some are hexagonal, so quartz is a famous example of that. You see a sort of a largely transparent or translucent hexagonal crystal. That's probably quartz. Quartz is really one of the most common minerals in the Earth's crust. There are octahedral structures, prismatic structures. Some of them are even round. There are all sorts of really interesting structures that crystals take. It should be noted that the habit of a crystal is not just determined by the mineral composition, although it is determined partly by that, but it's also determined by the growing environments. So minerals typically form over, crystal structures form over a period of time, and in order for the orderly arrangement of atoms or compounds to take shape, a certain amount of time is needed. If a sample of mineral is cooled very rapidly, for example, or is formed under very high pressure, it might not have the time or the sort of space to form its normal orderly lattice arrangement, and so it may adopt an amorphous structure, or it may adopt a different crystal lattice arrangement depending on the temperature and pressure and the time that it has to form. So the crystal habit and structure is not always purely a matter of the mineral composition, but also the growing environment. Another important property of minerals is called cleavage. So cleavage relates to the particular way in which a crystal structure will break, or preferentially breaks, or cleaves, in other words, planes of weakness in the crystal lattice. So this is formed by the fact that different minerals have different bonding arrangements, and some of these bonding arrangements lead to characteristic planes of weakness, so particular places or ways in which the crystal will tend to break, and this leads to characteristic planes of cleavage, which can be used to identify minerals. So a good example of this is micas. So micas have a characteristic two-dimensional arrangement, basically like layers on top of each other. And so those will tend to cleave, obviously, between the layers, because the bonding between the layers is much weaker than the bonding within a layer. Whereas something like diamond has a three-dimensional structure, so it doesn't have that same sort of two-dimensional. So now that we've talked about some of the main properties of minerals, so there's the external appearance in terms of shape, which is the habit. There's cleavage planes, which relate in particular to the crystal structure, in terms of the symmetries that are present. There's hardness, which relates to its ability to avoid being scratched. Lustre, which is basically shining as color and streak. So now that we've gone over some of those properties, I want to talk a bit about some of the different mineral classes. So there are several thousand different types of minerals that are recognized. According to Wikipedia, over 5,000. Depends exactly how they've been classified. Basically, each mineral has its own specific chemical composition. So that is a specific arrangement of specific ratios of atoms in regular patterns constitute a mineral. And if the atoms are different or in different ratios, then it's a different mineral. There are some exceptions to that where you can have sort of variable proportions, but basically that's how it works. And again, that's different to a rock, which we'll get to later, that don't have a specific chemical composition. Now, the different mineral classes are basically determined by the composition, as you would expect, because the composition in turn will determine the chemical composition in turn determines the physical properties that we mentioned earlier. The Earth's crust, where basically the minerals that we know and study are found, is comprised mostly of silicon and oxygen. Oxygen, we know that's in the atmosphere, but it's also in the crust. Silicon is the element that's used to make a lot of electronic components because it's used for semiconductor. It's the main component of sand and, well, really most rocks. Silicon is everywhere. It's just below carbon on the periodic table in terms of it's in the same group but one row down. So that leads us to the most important class of minerals by far and away. Something like 90-95% of minerals that make up rocks and in terms of by mass composition of the crust are silicate minerals. So if you go around and pick up a random rock, it's almost certainly made mostly of silicate minerals. That leads us to talk about what distinguishes the silicate mineral structure or class, which is the silicate ion or silica. Now this is comprised of a single silicon atom surrounded on four sides in a tetragonal structure by oxygen atoms. So it forms a tetragonal pyramid, basically. So although all of the sides are equal, so because it's symmetrical, it's a little bit hard to explain. If you just do a Google search for silicate ion, you'll see what it looks like. Again, I'll post this on the Facebook. There's basically four oxygen atoms spread equally around a central silicon atom. So a silicon ion has a charge of +4 because it loses its 4 valence electrons. It has the same number of valence electrons as carbon, and then it binds to 4 oxygen ions, which have a charge of -2. Basically, because oxygen is a very strong oxidant, so it tends to grab onto electrons. So it tends to form a -2 charge. It has a deficiency of 2 electrons in its valence shell, so when it fills up its valence shell, it will have a charge of -2. So when you have 4 oxygen atoms surrounding a central silicon ion, the entire unit, the silicate ion, will have a charge of -4. So you can't just have you can't just mush a bunch of silicate ions together, because the entire resulting structure would have an enormous minus charge, which isn't stable. So there's a few ways that silicate ions combine together to form silicate minerals. And basically the class of silicate minerals is comprised of just different arrangements of these silicate ions, so the tetragonal structures, combining together in different ways with themselves and also with other substances or with other elements, compounds. So the main different classes of silicate minerals are defined by I suppose you could think of it as the dimensionality of the structure of the silicate ions with respect to each other. So you can have isolated tetrahedra, and in order to balance out the charge, you'll need to have positively charged ions spread throughout the lattice as well. So typically those can be magnesium or iron or other metals like that. Metals are typically positively charged when they're in the ionic form. And so that's olivine. Olivine is comprised of single tetrahedron units with the charge balanced out by cations. It doesn't have any cleavage planes because there's no characteristic planes of weakness. Pyroxene are basically single chains of silica joined together. And the way that works is, if you think of, remember that we have a central silicon atom surrounded by 4 oxygen ions. Well, if you put another silicon ion next to it, it can share some of those oxygens with the next one, which can in turn share more on the other side with the oxygen, with the silicon next to that, and so on and so on. So you can form a chain. That reduces the overall ratio of oxygen to silicon, because you're basically doubling up on using the same oxygen for 2 different silicon. So you don't need as many positively charged cations. Those tend to have, so these pyroxenes tend to have 2 planes of cleavage at right angles, because there are the single chains and then there are the 2 dimensions that don't have the chain structure. Amphiboles are the next class, so they're double chains, basically the same as pyroxenes, except there are 2 chains rather than 1. Micas, which I've already mentioned, form sheets. So instead of just sharing oxygens between silica in 1 dimension along a line, they share it in 2 dimensions. So they form planes. So those have a single plane of cleavage, basically along the plane of the between the planes of the sheets, where the bonding is weakest. So these still need to have cations to offset the negative charge, but they don't need as many again, because the oxygen ions are being shared by more silicons, thereby reducing the total amount of negative charge that has to be offset. Next class of feldspars. So these are 3-dimensional networks of silicate ions, where the oxygens are shared in 3 dimensions instead of only 2 in the case of the sheets, in the case of the micas. Feldspars, though, still have some cations offsetting the negative charge, because there's still some residual charge there. In particular, potassium and aluminium are fairly common in the feldspars, as well as the micas. Quartz is the final class of silicate minerals, and it is comprised purely of silicon dioxide. So there are no cations, at least in pure quartz, and it's purely a 3-dimensional lattice where all of the oxygen ions are shared between surrounding silica. So it's a very simple structure. Quartz is also the most common single mineral in the Earth's crust, I believe, and it's a very common component of rocks. As I said, if you find hexagonal, largely translucent crystals, those are probably quartz, very common. And it's because its constituents, silicon and oxygen, are very common as well. So basically, you can think about the silicate groups as starting from independent tetrahedra, which have a 4:1 oxygen to silicon ratio, and then a continual decline of the relative amount of oxygen as more and more oxygens are shared between silica, until you reach quartz, which has a 2:1 oxygen to silicon ratio, and therefore doesn't need any offsetting cations to balance out the negative charge. You can see in this simple example how the mineral structure leads directly to properties like cleavage, for example, because the dimensionality of the sharing of oxygens with surrounding silica, whether it's chains or sheets or 3 dimensions frameworks, determines what sort of cleavage planes the resulting crystal has. You can also imagine how that's going to also affect things like the lustre and habit and other crystal properties. So those are the silicates. They're the most common, most abundant, and most important type of minerals. So the different classes that I mentioned, olivine, pyroxene, amphibole, micas, feldspars, and quartz, but many of those have multiple different types of minerals within them. So, for example, feldspars come in orthoclase and plagioclase forms, depending on mostly the cations that are offsetting the negative charge and exactly what structure and arrangement they're in. And there are many, many different types of these. So these are classes, not specific minerals that I've been talking about. Having discussed the main classes of minerals, There's one other specific class of silicate which I want to discuss before moving on to the non-silicate minerals, and these are the so-called phyllosilicates. They're a class of sheet minerals, so they're sort of like, they have a mica-like structure. They're sheets. The reason these are important is because clay minerals are a type of phyllosilicate. Clay minerals are a particular type of phyllosilicates, which are hydrous, so they're hydrated. They have water associated with the structure, and they're particularly important because clay minerals are characteristic of soil. So soils are basically defined as clay minerals combined with organic components. We'll talk more about this hopefully in a future episode if I talk more about soil. But I think it's interesting that even a basic understanding of the structure of silicates and the classification can give one a sense of what is different about a clay mineral, and therefore why soil is so characteristic. Clay minerals have a lot of very interesting properties which make them very useful for growing in and suitable for plant development, basically. We'll talk about that later, hopefully. They're also thought to have been important in abiogenesis, the beginning of life, so they're very closely associated with living organisms in a number of ways. So I just wanted to mention those. Now it's time to move on to the non-silicate minerals. So again, there are many thousands of these, but I'm just going to talk about the broad groups, classes of minerals. The main ones that I want to discuss are the carbonates, sulfides, oxides, sulfates, halides, and native elements. So you can see that really the way that minerals are grouped is by a characteristic element that's present in their structure or compound. So in the case of silicates, it's the silicate ion, the SiO4 structure, which is found in all silicates. In the case of carbonates, it's the CO3 carbonate compound, which is characteristic of carbonate minerals. Carbonates are particularly important. They're typically formed, they're often biogenic minerals. That is, they're formed by the dissolution and subsequent crystallization out of solution of carbonate, which is a compound that's commonly found in the shells of marine organisms. So when these die, the calcium carbonate can often is dissolved, and later it may recrystallize through various means, forming carbonate minerals. One common instance of carbonate minerals that people may be familiar with is found in caves. So the famous cave structures, stalactites and stalagmites, these are carbonates. They're formed by calcium carbonate precipitating out of water and forming these structures. Basically, as they drip down the calcium, as the water drips on a small protuberance in a rock, the calcium carbonate can precipitate out, forming carbonate minerals, rocks basically, and then elongating the protuberance, leading it to extend further and further down or up sometimes. So calcium carbonate's the main constituent of limestone and other rocks like that. And these minerals often look quite beautiful. So marble is a form of limestone, basically. It's formed by limestone that's been subject to metamorphic pressures, loosely speaking, and it's often used in building. The trouble with carbonates, and including limestone and marble, is that they react very readily with acid, which is a diagnostic criteria actually, and that means that they are quite susceptible to erosion, acid rain, and other things like that. So they're actually not great as building materials, even though they look quite nice. Sulfates contain a sulfate ion, which is SO4 2-. They're commonly formed as evaporites, so that's sort of what's left over when salty water evaporates, basically. Oxides are a very important class of minerals. They're defined by the presence of oxygen, basically, particularly the O2 anion. Typically what happens is the oxygen is as mentioned, a very strong oxidizer, so it likes to grab on to electrons, basically. And so it will tend to form compounds with elements that are reducing agents, basically, meaning that they tend to give up electrons. And these elements that are good reducing agents, that are good at giving up electrons, are typically metals. So metals form positively charged cations, which, as I mentioned earlier, and so they form a natural pair to the negatively charged oxide compound. So oxides are typically basically metal cations combined, neutralized out, the charge neutralized out by combining with oxygen in various ratios depending on the charge and other factors. So corundum is an oxide. It's an aluminium oxide, so it's actually just comprised of aluminium combined with oxygen. Many of the ores that we use to extract metals, so like aluminium for example, or iron, are oxides, typically because these metals readily combine with oxygen. So that's actually what happens when an iron substance rusts. Pure iron is unstable in atmospheric conditions, so it tends to react with oxygen to form. So many metals are like this. They'll tend to react with atmospheric oxygen to form oxide, basically. And these are the ore forms that we mine and then purify to obtain these minerals. So oxides have quite a lot of economic value because of the metals that they contain. Sulfides are a class that includes sulfide ions, so including pyrite that I mentioned earlier. That's iron sulfide. Pyrite has a brassy color which looks a little bit like gold, sort of a pale yellow, and so can be known as fool's gold. If you see rocks that have sort of small flecks of brassy, pale, yellowish looking substances, that's probably not gold, it's probably pyrite. Gold is actually much more impressive than pyrite if you compare them next to each other, but anyway. And finally, the last class that I wanted to talk about second last class actually, halides. So these include halogens, fluorine, chlorine, iodine, bromine as the main anion, so negatively charged metal there. So fluorite and halite, not to be confused with the class name halide, which is sodium chloride table salt. That's actually a mineral, halite, because it includes chloride. Fluorite, similar, includes fluorine. These are often formed as evaporite, so again, what's sort of left over when water evaporates. They also have important economic uses, obviously. The very last class that I want to talk about are the so-called native elements. So these are probably the easiest to recognize and understand because they have the simplest chemical structure. The native element is just a single element by itself, not bound or bonded to anything else. There are not many native elements that are found naturally, and they have to be found naturally because otherwise they're not considered minerals. But there are a few. So a diamond is one. Diamond can be found naturally, and it has a regular crystalline lattice arrangement, and it's formed completely of carbon, just carbon arranged in a particular lattice structure. So that's a mineral in a native element. Gold and silver are two other prominent examples, so they can be found in their native form. The reason that they're not typically found, or particularly gold is pretty much never found bound to anything else, is because they're fairly inert, especially gold. They don't really react very readily with other things like oxygen, for example. So they're just found in native form, which makes mining for gold and silver easier in some sense than mining for iron or aluminium, which have to be extracted often at great cost. Or historically at great cost anyway, from the oxygen and other elements that might be found in their ores. So that exhausts the major mineral classes that I wanted to discuss. Obviously there's a lot more detail to go into there. Briefly now, I want to just look at the three main types of, talk about what rocks are, and then the three main types of rocks. I want to go into even less detail here than I did with minerals, because there's a lot more to say about rocks, in particular because different types of rocks are associated with different geological processes in a way that's not as directly relevant to minerals. And so they're more readily discussed in detail when I discuss, for example, volcanoes in the context of igneous rocks, and various erosion and deposition processes when I discuss sedimentary rocks, tectonic plates when I discuss metamorphic rocks. So I don't want to go into a very large amount of detail here because they're naturally discussed in other settings, but I do want to introduce the concept of rock and briefly discuss the main classes. So what is a rock? I mean, we think we all know what rocks are. Interesting thought exercise is to imagine how you would define a rock to someone who's never seen one before. Not as easy as you might think. So in geology, a rock is a naturally occurring solid aggregate of one or more minerals, or sometimes mineraloids, which are basically mineraloids are substances that meet some but not all of the 4 characteristics of minerals that we mentioned earlier, but I'm not too interested in that. Basically, they're formed of, so basically rocks are solid aggregates formed of minerals. Aggregate means they're sort of just combined together. Rocks don't have a specific chemical composition. So if I tell you this is a mineral, you can legitimately ask me to write down the chemical formula for that mineral, because it must have one if it's a mineral. Sometimes it's simple, sometimes they're very complicated, but they must have one. If I asked you to write down the chemical formula of a rock, you would legitimately just look at me confused, because rocks don't have, or at least in general, don't have specific chemical formula. That's the main difference between a rock and a mineral. Rocks can be made out of many different minerals. So they're a sort of a level up in organization, as I mentioned earlier, from minerals, if you want to think of it that way. Of course, a rock could be made of a single mineral. A rock could even be made of a single element. You could have a rock which is basically pure 100% gold, for example, a gold nugget. That's basically a rock that's only one element. Those are pretty rare, though, but it's possible. Now, as I mentioned, there are 3 different types of rocks: igneous, sedimentary, and metamorphic. Now, again, this may be slightly heretical. It's my opinion that the boundaries between these 3 types of rocks are more conventional than absolute. So, as we'll see, hopefully in future episodes, if I get around to talking about the processes that go to forming sedimentary, metamorphic, and igneous rocks, really there's a bit of a fuzzy boundary between them. There's a bit of a fuzzy boundary between a sedimentary and a metamorphic rock, a metamorphic and an igneous rock. But nonetheless, it's still very useful to talk about the 3 classes, because in most cases it's fairly clear which class a given rock falls in. An igneous rock comes from a Latin word for fire, forms through the cooling and solidification of magma, or lava. Basically, magma or lava is just molten rock. Magma is under the Earth's surface, lava is on the surface of the Earth. It's just molten rock, literally in a liquid form. When magma solidifies, or lava solidifies, it forms an igneous rock. The particular structure and composition of an igneous rock is determined mostly by the temperature and pressure at which it solidifies, and also the time span at which it solidifies or crystallizes. Most igneous rocks are comprised mostly of silicate minerals. That applies to most rocks, I suppose, but especially igneous rocks, because most of the Earth's crust is comprised of silicates, so it's not surprising that the rocks we get out of it are, when the magma crystallizes, are highly silicate enriched. Mostly the classification within igneous rocks is dependent upon how much silicate is in it. So so-called granitic rocks are relatively enriched in silica. So-called basalt rocks are relatively deficient in silica, and andesitic rocks are in between. When I say enriched and deficient, it's important to bear in mind that even basaltic rocks have like 50% plus silica usually. It's just that andesitic and granitic rocks have even more, like 60-70%. So it's to do with how much silica, but they all have a fairly large amount of silica. That's why I said if you just pick up a random rock, it's probably mostly made of silica, because of silicate minerals, because they're just that common. So volcanoes, when they spew out lava and that crystallizes, solidifies, that's an igneous rock. Moving on to sedimentary rocks. These are the most common rock that you probably see if you just pick up a random rock on the Earth's surface, although it does depend where you live. Sedimentary rocks are formed by sedimentary processes, so they're formed on the Earth's surface by the accumulation and sedimentation of fragments of other rocks and minerals, and sometimes organisms as well. So fossils are only found in sedimentary rocks, for example. Sedimentary rocks are always made of previous rocks, so ultimately you can think of everything derived from an igneous rock at some point. I guess, if only because if you go far enough back in time, all of the Earth's surface was molten and there were no solid rocks. So the first of those that crystallized were the first igneous rocks, and then when weather processes began to break up those igneous rocks and transport them and reform them, sediment them, and combine them together into the first sedimentary rocks, then we have the first sedimentary rocks, and so on. The classification within sedimentary rocks is mostly determined by the size of the particles that come together to form sediment, so anything from big boulders to tiny clay particles and in between, and also the process that, I guess, combines them together. So you can have chemical precipitants, so basically the water evaporates, leaving chemical evaporate rocks behind, or you can have temperature and pressure, can have plastic sedimentary rocks. So there are different processes that can lead to sedimentary rock formation. But sedimentary rocks are basically products of erosion and transportation through weathering processes, in particular wind, water, ice, glaciers, and also mass movement, so mass wastage, that's the gravity basically, and also biological processes. So tree roots, for example, can break up rocks, and animals can dig and things like that. So all of these processes lead to the formation of sedimentary rocks. Fossilization, as I mentioned, also considered sedimentary rocks. Final type of rock, the metamorphic rocks. Metamorphic rocks are formed by subjecting any type of rock, including sedimentary, igneous, or another metamorphic rock, to sufficient temperature and pressure, which lead to a change in the not the chemical composition, but the chemical structure of the rock. So metamorphism basically means change in form, and that's what happens to a metamorphic rock. It changes in form, but generally not in composition. Now, it's important to note, if you subject a rock to high enough temperatures and pressure, it will melt. If it melts and then recrystallizes, it's an igneous rock. It's not a metamorphic rock. In order for a rock to be igneous, it must melt. If it does not quite melt, if it's subjected to temperature and pressure, which can cause it to start to flow, to become plastic, but doesn't melt, then it gives rise to what we call a metamorphic rock. So you can see how there's scope for sort of a gray zone where it like partially melts but doesn't completely melt. So the classification of metamorphic rocks is usually based on how metamorphized they were. We talk about the grade of metamorphism. So basically, the higher temperature and pressure and the longer that they were subjected to it, the higher the grade of the metamorphic rock, and the more foliated they tend to become. Foliated meaning that you can observe distinct bands within the rock, and those tend to occur as a result of significant pressure and temperature. There are non-foliated metamorphic rocks like marble, but many metamorphic rocks are foliated, so if you see those foliations, that can be a sign of metamorphic rocks. And the more distinctive they are, typically the higher grade they are. So those are the three classes of rocks, and a little bit about how they form and how they're classified. There's obviously a lot more to say there, which hopefully will be left to future episodes. So before wrapping up, there's just one brief little final topic that I wanted to discuss, which relates to how the different rock types are related to each other. And this is called the rock cycle, which you may have heard of before. It's also something that seems to be taught quite a lot. So the rock cycle just explains the relationship between the different types of rocks. Now, it's important not to think of it as some sort of determinate cycle. Rocks don't have to go around in any one direction, or necessarily will ever move beyond one form that they're in. I mean, it depends on what physical processes are operating, what environment they're in. The point is, though, that rocks or minerals that comprise them can cycle between a number of different forms, basically magma, igneous rocks, sedimentary rocks, and metamorphic rocks. And there are particular processes that interrelate those forms. So we've already mentioned a number of them. We'll start with an igneous rock. Actually, we'll start with magma. That's a more natural standpoint, a starting point, because that's the form that minerals take in the Earth's mantle, or at least parts of the Earth's mantle. So magma, basically liquid minerals. When those cool, they crystallize, solidify to form an igneous rock. Now, if you melt that, it can go back to form a magma, or if you heat it and subject to it sufficient pressure, but such that it doesn't melt, but it changes its structure or form, that forms a metamorphic rock. And you can, of course, melt a metamorphic rock back to a magma. You can melt anything back to a magma. Although typically you don't melt a sedimentary rock directly to a magma, because first it will metamorphize and then it will melt. We've got, at the moment, igneous and metamorphic rocks, which can melt to magmas. Magma can't cool directly to a metamorphic rock because it cools to an igneous rock, and which then, subject to heat and pressure, can become a metamorphic rock. But what about sedimentary rocks? How do they fit in? Well, both metamorphic and igneous rocks, either of those can be subject to weathering and erosion effects, I mentioned before, which form sediments. Sediments themselves aren't rocks, they're sort of fragments of rocks, if you want to think of it that way, which then, through further processes, sedimenting and compactation processes, form sedimentary rocks. Sedimentary rocks, in turn, can also be subject to weathering and erosion to form new sediments and then new sedimentary rocks. Or they can be subject to heat and pressure to form metamorphic and then finally melt to form magma. So that's the relationship between the three different rock types. And again, this shouldn't be thought of as a deterministic cycle. I mean, a given mineral substance can just sit as a metamorphic rock for 1 billion years, and that's perfectly fine. But it just describes the relationships between the different types of rocks. And there's obviously a lot more to say there about how and when each of these processes takes place, but that's for a future episode. So that concludes what I wanted to say today. I wanted to finish out the episode with just a brief announcement, I suppose, or explanation about the podcast and its future. So you may have noticed that there hasn't been an episode in about 6 months. That's pretty poor form on my part. I apologize for that. The reason for this is that I've been unusually busy lately, and unfortunately the podcast has had to take a back seat. When I first started the podcast, which is over 5 years ago now, unbelievably, I wasn't as busy as I am now. I didn't have as many additional commitments, so at the moment I am still studying, and I've actually taken on more subjects than I had in the past, over the summer and other times like that, which keeps me busier. But I'm also working part-time. I'm involved in a couple of clubs at university and elsewhere. I write on a blog periodically, and I'm also, my newest project is I'm writing a book. This book unfortunately doesn't really have much to do with the podcast, although there might be 1 or 2 episodes I could get out of it, because some of it does relate to cosmology. So for the most part, the reading that I do for the blog and podcast are not related to each other, or the book and the podcast. The book and the blog that I write are mostly related to basically philosophical questions, and particularly about religion, which I'm quite interested in. You can check out my blog at thegodlesstheist.com if you're interested in that. But unfortunately, it doesn't relate directly to the podcast, so it means that there's a certain diversion of resources. Now, what I will do is ensure that the past episodes are always accessible on the website, so those are always going to be up. So I encourage people to go back there, listen to past episodes. There's a wealth of material there. The episodes are designed to be timeless. There's no real news material or anything that gets out of date there for the most part. And also there is plenty of content within each episode, so I've designed them so that they can have re-listening value, particularly 6 months, a year later, you can re-listen to them, and it's a good way of revising material. The podcasts are really designed to be a learning aid and to help people be exposed to new knowledge, so that's what I've made them for. So please continue to take advantage of them and stay subscribed if you are. There's no cost to staying subscribed. In terms of the future of the podcast, in terms of new content, I've decided that what I'll do is commit to producing a new episode every 3 to 4 months, which is not especially regular, I know. So it can be thought of as a continuation of the current sort of quasi-dormant status. But it's not completely dormant. I want to have a little bit of new content dribbling out occasionally. Please feel free to continue emailing me. Someone brought to my attention that one past episode wasn't working properly in terms of downloading it. I still don't know why that happened, but I was able to re-upload it and fix that. So if there are any issues like that, please bring them to my attention. You can contact me at fods12@gmail.com. That's FODS12@gmail.com. Thank you for your continued support. I do hope in the future, maybe a year, 2 years down the road, to continue more regular production of episodes if I have more time and some of my other projects free up some time for me. I have many more episodes that I'd like to produce, so there's easily another 100 episodes that I could do in terms of content, but it does take a certain amount of time, which I just don't have at the moment, unfortunately. So, thanks for listening. Talk to you next time.